Yeah. I don't know.
I think it's
Do I?
Alright. I think it's recording.
You're checked out. You're on the list.
Yeah, it's
Do I
recording.
just say yes?
Okay.
You're on the list.
So a couple of things. If some of you already signed up, but there's a science show with the Mesa Elementary. If you need hours, or if you just want to hang out and do science with your kids, that'll be that. So, all right. Let's talk about this KSP lab, because a lot of this is going to be on the test on Monday. Okay, just make sure everybody's cool with what's going on. So here's the whole point of these calculations and what they mean. First off, when you look at any KSP value, and this is the recurring theme, and this is how it ties into Ka values. So if you look at how Ka values are calculated, okay? So Ka values come from some acid turning into a hydrogen.
You can't see it.
God, what do you want? The world? Seriously?
That's just
Psychic?
weird.
Can you not visualize in my mind what I'm thinking?
I'm already in your mind.
We're in your head.
I'm there.
Okay.
You're thinking the number 7.
Yeah. I live.
I'm thinking the number what?
7.
Oh, so far from that.
67.
Oh, even worse. Okay, there. That's what I was thinking. None of you guessed that. So here's the story. So if you, there's the math side of it, and then there's the chemistry side of it. So the math side of it says, hey, Ka is some hydronium ion concentration over H over anion over HA. Old school, right? And we can talk about the concentration of all three of these because the acid is a solution. Okay? You can talk about the molarity of that. You can talk about your hydronium ion concentration and your anion concentration. Great, you can talk about all that. Now, if you look at all the charts of Ka values, are they all big numbers or are they all small numbers?
Small.
They're all small numbers. And later on, you'll see from the thermodynamic perspective why this works. But any time you have a Ka less than 1, okay, any K value, KSP, Ka, Kb, whatever it is, as long as that K value is less than 1, the forward reaction is not favored. Okay? It's not. It doesn't work. So, conceptually, hey, if you have a K value less than 1, it's not going to go in that direction. It can a little bit, but that isn't the predominant form of it. So there's like the chemistry side of it. The mathematical side of it says the other way that you can produce a small Ka value is if you have a small hydronium ion concentration and you have a small anion concentration. Okay? Which again reinforces the idea that the forward reaction is not favored. Now, you contrast that for the Ka of strong acid, like hydrochloric acid, which is hydroniums and your chloride ions. Now, that Ka value would be much, much, much bigger than 1 because you're going to produce a lot of hydronium ions, you're going to produce a lot of chloride ions, and have very little of the molecular form left. So, there's that. And the reason that it happens is because if you have a weak acid, it has a strong conjugate base, and it wants to reform that acid. If it's a strong acid, this chloride ion has no desire whatsoever to reform the molecular form and make HCl, okay? Because they're more stable separates. So this is how this fits with KSP. So let's say, for example, you're looking at on number 11, okay? So you got copper nitrate mixed with sodium hydroxide to precipitate form. Copper hydroxide concentration of 4.8 times 10 to the 8. So here's where this is similar, but yet here's how this is different. So in this situation, you're making CuOH2. And what tries to happen is that tries to ionize into copper ions and 2 hydroxide ions. Okay? That's what this stuff is trying to do. So again, the story is not the precipitant. The story is the solution that's up above. So this KSP value, I gave it to you on the problem, is 4.8 times 10 to the negative 20. That's a really, 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 really small number. Okay? Now, here's the difference on how you calculate KSP. It's still products over reactants. So that KSP is going to be that copper ion concentration times the hydroxide ion concentration squared. And we're going to square that because there's a 2 in front of it. Okay? So again, the only way that I can make numerically a very small value of 10 to the negative 20th is if these ion concentrations at equilibrium are exceptionally small numbers. That's the only way it works. Now, here's what's different with KSP. We don't divide by the concentration of the CuOH2. The reason that we don't divide by the concentration of that is because it's a solid chunk at the bottom of the beaker. Okay? The acid is floating around like the other anions. This stuff is chunky at the bottom. So on a particular level, you've got this precipitate down here, CuOH2. That's your precipitate bank. Okay? So up here, there's some copper ions, there's some hydroxide ions floating around. Now, we don't draw in the water molecules. Those are there, obviously, because without the water, you couldn't have this reaction take place. The water's there. It's vitally important. I'm not trying to diss on the water. It's vital. We just don't draw it because it just muddies the water. Okay? It's there. The copper ions are attracted to it. The hydroxide ions are attracted to it. We just don't draw it because we don't mess with it. Okay? Now, here's the story. So let's talk about number 11. So water is then added to the test tube, doubling the volume, but some precipitate is still observed in the bottom of the test tube. Okay? So the first thing you want to do is determine the molar solubility. So here's how this plays out, and kids tend to get this confused. Let me try and unconfuse this situation. Okay? So just like with an acid, you're going to have CuOH2 if you want to do a Rice chart, which is going to turn into copper ions and 2 hydroxides. Now, here's how this is similar to a Ka calculation. If you're not given the concentration of any of these ions, and you're given the KSP, so you know what the KSP is. Okay, you know what the KSP is. We're not trying to find the KSP. You know what the KSP is. So you know, because you're not given any information about the copper ions or concentration on the hydroxide ions, you're not given any of those. So you just assume that those start at 0. Cool. Okay? Now, I'm going to add some copper ions. It's going to be X. But instead of adding X hydroxide ions, how much am I going to add? 2X. So this is going to become 2X because I get twice as many, I get 2 hydroxide ions for every 1 copper ion. Okay? Just like a cheese sandwich. I get 2 slices of bread for every 1 slice of cheese. Okay? So this becomes X and this becomes 2X. Okay? And I do this because I don't know what they are. This is the only thing that I can do. So that KSP is going to equal that concentration of X times 2X squared. Okay? Now, if you go through the math, this becomes 4X cubed. Okay? So when you get that value of X, that's going to be a really small number. Okay? And that's going to be like 10 to the negative 7. Okay? It's an incredibly small number. Now, once you get X, which is around 2 times 10 to the minus 7, a couple of things you need to understand about this. That X represents the copper ion concentration. Okay? Now, you didn't have to find it, but I could have also said, hey, what's the hydroxide ion concentration? I could have asked you that. If I asked you for the hydroxide ion concentration, what would you do with that value?
You gotta double it.
You double it. Okay, hey, there would be your hydroxide ion concentration because that would be twice as much. Okay, I didn't ask you, but you could. So, how this is generated? Okay, you got to understand like the origins of this. Whatever this is also how much of the CuOH2 dissolved to create it. So just like if I had 5 sandwiches, okay, and I got, the only way that I could get 5 slices of cheese is if I had 5 sandwiches, okay? I would get 10 slices of bread because I had 5 sandwiches, okay? So if you know what X is, you know how much of the copper hydroxide had to dissolve to create that concentration, okay? Now, here's the most important part of part B, okay? It says water is then added to the test tube, doubling the volume, but some precipitate is still observed in the bottom of the test tube. So this is what I had you do in the lab yesterday, okay? So you had the test tube, and I think it was the one with magnesium hydroxide, okay? I'm trying to remember, I think that's right. And you had some magnesium hydroxide, and you added some water to it, okay? Now, here's the tendency that you tend to do. You say, oh, great, I doubled the volume, and let's say that had been a 0.1 molar solution of magnesium hydroxide, and I doubled the volume, and then you're tempted to say, oh, my new concentration would be 0.05 because I doubled the volume, which would seem reasonable. But there's a huge caveat to this question. The caveat to the question says, there's still some precipitate left down below. So what that means is that Mother Nature is still in equilibrium. Now, this is where you have to understand what this is calculated upon, okay? Your KSP, it's a simple thing, but it's vital to understanding this question. KSP is the concentrations multiplied together to get some value. So as long as you still see some precipitate in the bottom of that test tube, that means that these concentrations are still the same. They haven't changed. Now, but what did happen is this. Mother Nature goes, man, there's a lot of water, but I got to maintain the same equilibrium. I got to maintain the same concentrations. So what would Mother Nature have to do to the precipitate bank?
It'll take a little from it.
Yeah, you got to make a withdrawal. Okay? You have to make a withdrawal from the precipitate bank because you're increasing the volume, but you want the same concentration. So that would be like me having, hey, I got 16 kids in the front half of my room. So I have 16 kids here, and I'm in equilibrium. Now, I doubled the size of the room, but I still want the same concentration. So what would I have to do?
Add some more kids.
I got to bring in another 16 kids so that I maintain the same overall concentration. So imagine with this one, I'm making the room bigger, but I want the same number of kids per area. And that's what that molarity is. So if I make that bigger while I'm adding that volume, but I still see some precipitate, that means that it's still in equilibrium. Now, where this gets sketchier is if you add enough water and all of that dissolves, okay, and you don't see any precipitate. You can't figure out anything at that point, okay? You don't know. You don't know if it's exactly at equilibrium. You don't know that maybe I added so much water that it can't, like it all dissolved, and maybe that concentration is less than the equilibrium. You don't know. But as long as you see any type of precipitate, the concentrations are whatever it's going to be to create that equilibrium. Okay? That's the whole key. You see a precipitate, system's in equilibrium. So when you get to part 3, where you had the sodium hydroxide and the magnesium nitrate. So this was what was supposed to happen, okay? So you had that precipitate down here of magnesium hydroxide. But keep in mind, that isn't the story. The story are the magnesium ions and the hydroxide ions. That's the story. Okay? That's the story. So here's what was supposed to happen. You added some more magnesium chloride into that. Now, is magnesium chloride soluble or insoluble?
Still soluble. I like that.
Why would I not ask you to add an insoluble salt?
It would make no sense.
Yeah, oh, what would it do? It
Just
just sink to the bottom. Like, oh, that was cool. No, the whole point of this is that you're going to add the ions. The only way you can add the ions is if the stuff is soluble, right? Final answer. And all chlorides are soluble except for silver and lead. Okay, that's neither silver nor lead. Okay? So, I'm going to add some magnesium ions. Now, keep in mind, Mother Nature wants the magnesium ion concentration times the hydroxide ion concentration squared to equal some value. Mother Nature wants to be in equilibrium, right? Mother Nature gets chapped if you're out of equilibrium. So you're going to come in and you're going to add a bunch of magnesium ions. What's Mother Nature's response?
Sit the kids down.
Yeah, like, hey, kids, sit down. Okay? There's too many of you in the room. Chill out. Have a seat. Okay? Because we're out of equilibrium. So what should happen is that you should have seen an increase in the amount of precipitate. Because again, Mother Nature wants the same concentrations to be in equilibrium. So if you add too many ions to it, Mother Nature flips out and goes, add. We're going to make it precipitate. Okay? Now, in contrast to this, here's the contrasting side of this. On the beginning, on part 1, okay, you mix magnesium nitrate and potassium hydroxide. The very first reaction that you did, you had a precipitate of magnesium hydroxide. Okay, now here's what I want you to see the differences. And this is the diagram. There's a whole bunch of things that relate to this concept. So up above, you had some magnesium ions and you had some hydroxide ions. Okay? Again, the story is not the precipitate. The story is the ions. So you had some of these floating around. Okay? Not many, but you had some. Then you added hydrochloric acid. So you added HCl, a strong monoprotic acid. Soluble or insoluble? Okay, completely soluble. Okay? And it's going to ionize. Okay? So here's what's going to be important. I'm going to add a bunch of hydronium ions into you. Okay? I'm going to add hydronium ion. Are the hydronium ions going to react with the magnesium?
No way.
Absolutely not. Why?
They're positive.
They're both positively charged. They can care less. It's like, go away from me. This is way too positive. It's like you have two friends that are both really upbeat all the time, okay? But they might not like each other because they're like the same personality. It's like, go away. You both are too positive. Get away from me. Okay? But here comes the hydroxide. You put that hydronium in the presence of the hydroxide, you're going to make water. So here's what's important. So as a function of time, here's the concentration of the hydroxide ion. Okay? It's a certain value. You add hydronium ions. The hydroxide ion concentration is initially going to crash. Okay? Like Bitcoin. It's going to crash. Right? Okay? You're screwed. Because your Bitcoin investment is just crashed. But you got a bank though.
We can rob the bank.
Oh, that's not even rob. That they frown on that.
We're not robbing.
Okay, they frown on that. How about we just make a withdrawal? Right?
Oh, yeah.
I don't think
So the hydroxide ion concentration is crashing. Mother Nature goes, this is bad. So Mother Nature can do one of two things. Mother Nature could go outside the test tube and try and find hydroxides. Okay?
What?
Put up a help wanted sign. Hey, hydroxides wanted. Probably not going to get much of a response. Okay? Or what can Mother Nature do? Go to the bank and make it withdraw. Now, here's the thing though. Mother Nature, if on the particle side of this, magnesium hydroxide, okay, so you got chunky magnesium hydroxide. Can Mother Nature just go in and take the hydroxide?
Gotta take that.
No, 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 okay? Because then you just have magnesium ions left behind, which would be weird,
That'd be sad.
okay? It'd be sad. I don't know about that. So you got it. It's a part and parcel of the same thing. So you'd have to withdraw both of those. Because what does Mother Nature want to do?
Be in equilibrium.
Be in equilibrium. Okay? So on that second question, where it says make a sketch showing the system before the hydrochloric acid and the solute and the solution portion. All you have to do, okay, is go, hey, here's my chunky magnesium hydroxide, and I've got a bunch of magnesium ions floating around, and I have a bunch of hydroxide ions floating around. Okay, literally, that's all you have to do. Do not make this complicated. Okay, all you're trying to do is convince me that you understand that it isn't just the precipitate, that there's also hydroxide ions, and there's magnesium ions. Now, so this is before you add the hydrochloric acid. Literally, this is all that. Okay, if you want to shade it and make it look nice and color it, you can.
Extra credit?
No.
You really need extra credit.
Now, notice that I say before you hydrochloric acid is added. Now, on part B, make a second sketch showing the impact of adding the hydrochloric acid and show how that affects the amount of precipitate. So what do you think I'm going to look for in the second diagram in terms of the amount of precipitate that you have? It's going to become smaller. Okay? Why has it gotten smaller?
All you took out.
What? You made a withdrawal. Why?
To maintaining equilibrium.
Yeah.
Plus one's-
So now, you added the hydronium ion. So what did you make?
Water.
So now, if you wanted to get fancy, you could say, hey, we've made some water molecules. Okay? Right? Now, are there still some magnesium ions floating around?
Yes.
For sure. Are there still some hydroxide ions floating around?
Most definitely.
Most definitely. But we've made some water. Okay? We've made some water. But more importantly, show me that the amount of precipitate is less. Okay? All you're doing is graphically illustrating that, hey, I understand what's going on. There's some magnesium, there's some hydroxide. I add the hydronium ions, I make some water, the precipitate dissolves. Bada boom, bada boom. There you go. Okay. When you get to question number 3, question about the carbonate ion. Let me give you a hint. Look at the charge on a carbonate ion versus the charge on a hydroxide ion. Okay? Just think. When you get to number 4, solutions reduced in the formation of silver chloride precipitate. What, if any, changes are going to occur if you add hydrochloric acid? Let's talk about this. Here's your water. Maybe you mix silver nitrate and sodium chloride. Okay? You get a double displacement reaction. You mix silver nitrate and sodium chloride, and you're going to get sodium nitrate and AgCl. Again, all chlorides are soluble except for silver and lead. Okay, so you make a precipitate of silver chloride. So again, here's the story. You have a precipitate of silver chloride. What's in the solution up above? Silver ions and chloride ions. Okay? Now, do not get hung up on the hydronium ions. The hydronium ions for the hydrochloric acid aren't the story. Why aren't the hydronium ions the story? Here's hydrochloric acid. Why do you not, in this situation, why do we not care about the hydronium ions? Here's the story. Think about this. If I'm going to make the silver chloride, either make more or make less, what do I have to change? The number of silver ions or the number of chloride ions? That's it. Okay? That's it. If I add hydronium ions, are the hydronium ions going to interact with the silver ion?
No.
Nope, they're both positively charged. Not going to happen. Could care less. Are the silver or the chloride ions going to react with the hydronium ions to make the molecular form of hydrochloric acid?
No.
Absolutely not. Why not?
It's just its organic form.
It's a strong acid. It doesn't want to make it. It's not going to happen. Okay? Not part of the story. However, this is why I don't care about this. But I am going to add a bunch of chloride ions to it. So if I add HCl, what's going to happen to the concentration of the chloride ions?
Go up.
It's going to go up. What's Mother Nature going to do?
More PPT. Freak out.
Mother Nature's going to flip out. Why?
They don't like it.
He doesn't like it. Because Mother Nature has a specific Ka value for silver chloride, which is silver ion concentration times your chloride ion concentration. Okay? The story here is not the hydronium ion. The story is the fact that you added hydrochloric acid to it. Okay? And it's the chlorine ion concentration that's going to spike. So what's Mother Nature going to do?
Sit down.
Make precipitate. Okay? So you would see the precipitate. Okay? With that. Your answer to number 5 should be a really, really, really small number, like 10 to the negative 12 small. Your answer to number 6 would make a horrible GPA times 10 to the negative 9th. Your answers to 7A should be something times 10 to the minus 3rd. Your answer to 7B should be 10 to the negative 12th. And your answer to 7C should be 10 to the negative 5th. So it should go negative, on number 7, it should go negative 3rd, negative 12th, negative 5th. And the first two, A and B, would be horrible GPAs. So let's talk about the contrast between all of those on number 7. Okay? So on number 7, you got lanthanum fluoride. I've given you the KSP. It's an exceptionally small number. So here's the difference of what's going to happen on number 7. So on 7A, it's just LAF3 turning into lanthanum 3 plus 3 fluoride. Okay? That's how it's going to start. This is going to go 0, 0, X, 3X, X, 3X. Right? Cool. So, because there's a 3 in front of the fluoride ion concentration, what are you going to do with that? Cube it. So what you're going to have is the KSP
What happened, Bert? He's stumped.
like my stylus.
Can you use your finger?
I can shift it.
Okay, that's good.
Like it'll shift like to the eraser. It's weird because like it works on the left side. Like I can change that.
Reboot the page.
What if you just refresh it? Yeah.
You gotta refresh and refresh.
Okay, no, what happened?
Oh, but then the CEO.
This is what happens in the intermission.
No, you know what the CEO is. 2-tier.
Weird. Okay. All right. So back to our story. So you're going to have LAF3, F3, which is, so your KSP is going to be X times 3X, but the 3X is going to get
Squared.
cubed.
Oh, yeah, cube.
All right. So you do this, you get 27 X to the
Third.
Oh dear.
yay for algebra. Okay. Find X. Boom. That's also how much lanthanum chloride had to dissolve to create that amount. So the only thing that happens on when you get to 7B, now I've given you that it's 0.025 molar potassium fluoride. So instead of the fluoride ion concentration starting off at 0, now that's going to start off at 0.025. Now listen to me very carefully. Listen to me. This is a common mistake that's made. Do not do this. Okay? Lanthanum ions and your 3 fluoride ions. Okay? When I've given you on 7 that it's 0.025 potassium fluoride, that's 0.025, there's 2 things that you cannot do or don't want you to do. You don't have to multiply that by 3 to get the fluoride ion concentration. Okay? That is the fluoride ion concentration. Okay? You don't have to do anything with it. It's a gift. Accept it. Okay? Now, what you cannot do under any circumstances in this particular problem, to get the lanthanum ion concentration, you cannot take 0.025 and divide that by 3. Okay? You can't do that because you know what the KSP value is. The KSP value is a really, really, really small number. And I promise you, if you take 0.025 and cube it and take 0.025 divided by 3 and multiply it to get that KSP value, you're not going to get anywhere near 10 to the negative 19. Okay? So the only time, listen to me, the only time you could take this concentration and divide it by 3 is if you were trying to find the KSP value. If I had said, just to make the math easier, let's say that I said, hey, at equilibrium, your fluoride ion concentration is 0.027. And you're trying to calculate the KSP. You don't know what the KSP value is. If that's the case, and you were told that it was at equilibrium, you could take 0.027 and divide that by 3 to get your lanthanum ion concentration, and then you could mathematically calculate the KSP. But on this one, you are given the KSP. Okay? You know what that number is. So the only thing you know is the fluoride ion concentration. Do not multiply it by 3 to get 0.075. That's it. That's the concentration. Accept it. Do not overthink it. Accept it. Okay? Now, is this still, now is your lanthanum X? It is. Okay? But you know what the KSP value is. Now, when you get to 7C, I give you the fact that it's 0.15 molar lanthanum chloride. Okay? So, with that one, here's the difference. Now I'm giving you the lanthanum ion concentration, but this now is still 3x. So, on 7C, that KSP value is going to be whatever that concentration of lanthanum, 0.15, and that's going to be 3x. And not only is it going to be 3x, it's going to be what?